Welcome to lesson 9.1, Points, Lines, and Planes. So before we get into today's lesson, which builds off of some postulates and assumptions we've already used, and then gets into some new three-dimensional rules, what we want to keep in mind is all of chapter 9 relates to three-dimensional figures. So we've already worked a lot with two-dimensional figures on coordinate planes and doing our different transformations. Now we're moving into the three-dimensional figures. So it all begins with the ideas of points, lines, and planes. So the point, line, plane postulate. Expanded form. So you can see point, line, plane postulate. When we expanded it as A, B, C, D, and E for these assumptions. So first off, in today's notes, there's not a lot for you to write. So as we go through it, feel free to highlight, underline each parts of these postulates or assumptions to help you remember them. If you want to draw a picture off to the side, feel free. So first, in the point, line, plane postulate, it's the unique line assumption, which says through any 2 points, there's exactly one line. If the 2 points are in a plane, then the line containing them is in that plane. So remember in math, in 3D, we just have space. So a three-dimensional area we call space. A two-dimensional figure we're thinking of as a plane. And then lines go through those two-dimensional planes. Then we have the number line assumption, which states every line is a set of points that can be put to a one-to-one correspondence with real numbers, with any point on it corresponding to 0, any other point corresponding to 1. So basically what that says again is any line is a set of points that can be turned into a number line. Then we have our dimension assumption. Part 1 of that is that there are at least 2 points in space. Part 2 says given a line in the plane, there is at least 1 point in the plane that is not on that line. So if I look down here, if I had line AB in this plane, there's at least 1 point D that's not on that line in that plane. And then given any plane in space, so if I'm looking at my pink plane here in space, there is at least 1 point in space not on that plane. So point C out here would be at least 1 point in space not on the plane here that contains line AB and point D. Then we get to part D, the unique plane assumption. And that says through any 3 non-collinear points, there's exactly 1 plane. So through points A, B, and D here that are non-collinear, there's exactly 1 plane that contains them. And finally in this, part E, the intersection assumption, which states 2 different planes either do not intersect or intersect at exactly 1 line. So that all parts there, A, B, C, D, and E, are part of the point, line, plane postulate. Then we get down to the unique plane theorem, which states there's exactly 1 plane through a line and a point not on that line, shown here. So if we have line AB, point D not on that line, there's exactly 1 plane. If I wanted to use A, B, and point C, that would create a new unique plane through A, B, and C. Then we start to get into more of this three-dimensional idea. So it says the angle formed by a line and a plane is the angle of the smallest measure that the line makes with the rays in the plane from the point of intersection. So if we're looking at line here, or actually, let's use, line AB here. If we're looking at that, the angle formed by a line in a plane, it is the angle of the smallest measure that the line makes with the rays in the plane. So the rays in the plane would be ray AC, AD, and AE. And A is that point of intersection. So whichever one of those angles is the smallest angle from BAC, BAD, or BAE would be the angle formed by the line in the plane. We picked the smallest one. Then a line segment or a line or segment or array, there we go, that makes more sense. A line or segment or array is perpendicular to a plane if and only if the line and the plane intersect and the line is perpendicular to every line in that plane. So in order for a line, a segment, or array to be perpendicular to a plane, they have to intersect, and that line, segment, array has to be perpendicular to every line in the plane that passes through the point of intersection. Then, if one endpoint of the segment is in the plane, then that point of intersection is often called the foot of the segment in that plane. So if we're dealing with a line here, CD, that's perpendicular to my plane, and point D, that point of intersection, if that's my segment, CD, and D is on the plane, point D right there could be known as the foot of the segment. And then we have the line-plane perpendicular theorem, which states if a line is perpendicular to two different lines at their point of intersection, then it's perpendicular to the plane that contains those lines. So if a single line is perpendicular to two different ones at their point of intersection, then it's perpendicular to the plane that contains those other two lines. So again, not much to write for you, but a lot of different theorems, rules, vocabulary. Then we get into the next piece. Now you'll see where the orange star is here goes with the orange star of the image, blue with the blue, and then this kind of red goes with the red down below. But let's first look at this first paragraph. Two different planes are parallel planes if and only if they are identical, meaning they're the same plane, or they do not have a single point in common. So in this case, plane M and N do not have any points in common. They would be parallel planes. The distance between parallel planes is the length of the segment perpendicular to the planes with an endpoint in each. So in this case, the distance between our parallel planes M and N would be segment AB. Then we have the distance to a plane from a point not on it. So that's looking at this one here. Point C is not on plane Q. So the way we figure out that distance is measuring along the perpendicular segment from the point to the plane. So we would have to draw in the perpendicular segment here, C to D, and then we would measure the distance from C to that plane along that segment. And then a line is parallel to a plane if they do not intersect in a single point. So if the line never intersects the plane at a point, the line and the segment are parallel. And then we get into our final idea from these three images, which is the idea of skew lines. So it says two lines in space can intersect in exactly one point, be parallel, or be skew. Skew lines are lines that do not intersect and are not in the same plane. So if we look at the image here, line L is on our upper plane, M is on the lower plane. They never intersect, so they would be skew lines. Now let's start to make sense of this with an example. So example 1 says, use the cube at the right to match the item in the first column to its description in the second column. So first off, A says plane AFB and plane CHG. So AFB is the top plane here. We only need to name it with 3 points, but if we wanted to, it'd be AFEB. And then plane CHG, CHG is the bottom here. So the top and bottom would be parallel planes. So that would be option 6 here, letter A. They are 2 parallel planes. For B, line GH and plane ADF. ADF is this left side. GH is this back bottom. So GH and ADF show a line perpendicular. So GH here is perpendicular to that left side plane, which would be option 3 here. We know that this is a 90-degree angle because we were told it's a cube. So all of our sides intersect at 90 degrees. Part C, line EH and plane FBC. So plane FBC would be a diagonal plane in here, if we wanted to draw it in, FBC. And line EH is right back here. So EH and FBC are parallel. They would never cross, so it's a line parallel to a plane, option 4. In D, lines FE and BC. FE back up here, BC right here. So option D, they are skew lines. They never cross and they're on different planes. E, plane EBC and plane DGH is going to be 2 intersecting planes. EBC, the side here, and DGH, the bottom, intersect at the line CH over here. And then line FE and line AB are option 2 parallel lines. FE on the back top, AB on the front top, go on forever, never intersect on the same plane, so they're parallel lines. Then we move on to kind of our final ideas for this lesson. So it says, recall from previous lessons that when 2 lines intersect at a point, 4 angles are formed. So you can see right here. The point of intersection is called a common vertex. So 2 lines form 4 angles, and the point where they cross is our common vertex for all 4 of the angles. Then if you think about it in the same way, when we have 2 different planes intersecting, they create what are known as 4 dihedral angles. And those are formed by adjacent half planes and the line of intersection. So if we intersected this line here, one of our angles created would be from this half plane coming down and then this way. So where this blue angle is. The pink angle would create one, then pink to blue here, and blue to pink down here. So we have 4 dihedral angles. The line of intersection of these planes is known as the edge of the dihedral angle. So right here, this line would be the edge of all of our dihedral angles. Then how do we measure these dihedral angles? Well, they're measured in the following way. Suppose planes X and Y, which we see here, plane X, plane Y, intersect at line L. So line L right here. So what you would do is you'd pick a point anywhere on line L that you can see inside the planes or on the planes. So they use point P. Then you would draw a segment or a ray, PD, that's perpendicular to L in plane X. Then you would draw ray PC that's perpendicular to L in plane Y. So you would draw one in one plane that's perpendicular and one ray in the other that's perpendicular. Then the measure of the dihedral angles are the measures of the four angles formed by line PC. So if we extend that, line PC and line PD. So the measure of the four different angles, which would be DPC here, CP, whatever letter we'd put down here, then along this one here to P down, and then D to P this way. If PC is perpendicular to PD, so if PC and PD are perpendicular, then the planes are also perpendicular. So two planes are perpendicular planes if and only if they form a 90-degree dihedral angle. So, with this lesson being a lot of just vocabulary highlighting and filling in a few parts in the notes, what I'd recommend doing for this lesson is after you go through this notes, I would take a few minutes to read the lesson part in your book before you move into the practice problems for today. Because it's so vocabulary and theory heavy, it would help your understanding to take a few minutes just to read through that lesson on those few pages before the practice problems.